the James Webb Space Telescope's groundbreaking discoveries. The James Webb Space Telescope has recently uncovered new insights regarding the events that occurred before the Big Bang, challenging some existing scientific theories. The Big Bang theory suggests that the universe began from an extremely hot and dense point, which then expanded and cooled, allowing for the formation of stars, galaxies, and other structures. This theory is supported by evidence such as Hubble's law, which demonstrates that distant galaxies are moving away from us, implying that the universe is expanding. The age of the universe is estimated to be approximately 13.8 billion years. However, the James Webb Space Telescope has made an exciting breakthrough in understanding what might have transpired prior to the Big Bang. The cosmic microwave background and early universe. But what exactly happened before this momentous event? The cosmic microwave background, CMB, radiation is a faint radiation that permeates the entire sky. It is a remnant of the intense heat and light from the early universe. The CMB's uniform temperature is approximately 2.7 Kelvin, with subtle fluctuations that reflect density variations in the early plasma. The CMB also reveals that the universe was opaque to light until around 380,000 years after the Big Bang, when atoms formed, allowing light to travel freely. The proportions of primordial elements like hydrogen, lithium, boron, and beryllium align with the predictions of Big Bang nucleosynthesis. The arrangement of galaxies mirrors how matter has clumped together under the force of gravity over time, forming stars and galaxies from tiny fluctuations. The oldest galaxies are found at the farthest reaches of the observable universe, while younger galaxies are closer to us. Galaxies exhibit a range of shapes, sizes, ages, and compositions, which vary based on their location and history. Younger galaxies are positioned nearer to our location, while the oldest galaxies exist at the outermost edges of the observable universe. Theories about what happened before the Big Bang. The question of what happened before the Big Bang remains one of the most profound challenges in cosmology. The Big Bang theory itself describes the universe's origin from a hot, dense state that expanded and cooled over time. However, it does not offer an explanation for the cause of this event or what might have preceded it. Several theories have been proposed to explain the origin of the universe, such as the cyclic model, the periodic model, and the pre-Big Bang scenario. Each of these theories suggests different events and causes that led to the birth of the universe. The pre-Big Bang theory is tied to string theory, a framework that attempts to unify all natural forces and particles. In contrast, the boundaryless model posits that the universe has no boundaries in space or time, with the Big Bang being a soft beginning. According to this model, the birth of the cosmos can be seen as a quantum fluctuation from nothing, using quantum mechanics as a wave function to describe the potential histories that determine the universe's structure and properties. It's crucial to understand that these possibilities are not mutually exclusive and may complement each other in certain ways. The latest breakthroughs and what they mean. One of the primary objectives in cosmology is to uncover how the universe came into existence. The latest discovery made by the James Webb Space Telescope, the detection of the most distant galaxy cluster ever observed, may help scientists get closer to answering this question. In theoretical terms, the universe follows a hierarchical structure with matter and energy initially dispersed throughout space in a uniform pattern. Small perturbations were superimposed on this background, caused by cosmic inflation that occurred before and set the stage for the Big Bang. These fluctuations exist on all cosmic scales, from the smallest to the largest, as matter and radiation interact and the universe expands. Fluctuations in the density of time can be observed in the smallest and intermediate scales, with peaks and valleys appearing in the cosmic structure. Gravity and cosmic structures. The largest fluctuations can be detected in the CMB, which contains vital information about dense regions that began to develop under gravitational forces. Gravity doesn't act uniformly throughout the universe. Its effects are limited by the speed of light. This means that an overdense region will only attract nearby matter at any given time. The farther away matter is, the longer it will take for gravitational forces to be felt. The scale of these cosmic structures grows as gravitational forces cause star clusters, galaxies, and even larger groups and galaxy clusters to form. Once a large-scale region experiences enough gravitational attraction, gravitational collapse leads to the formation of bound structures. The initial formations to collapse include molecular clouds, dust, gas, atoms, and dark matter, which eventually give rise to the first stars and star clusters. The densest regions of space can take up to 200 million years to collapse, while areas with higher initial density can collapse much faster in as little as 50 to 100 million years. Star formation emits radiation and winds, which lead to complex environments that make it difficult to predict the details of these early structures. Galaxy formation and evolution. The first massive galaxies formed from the merger of these early structures. Galaxies were observed approximately 320 million years after the Big Bang, and the James Webb Telescope is expected to reveal populations of pristine stars in early galaxies on a broader cosmic scale. However, the physics of individual galaxies plays a minimal role in the formation of large-scale cosmic structures. The growth of galaxies and clusters of galaxies is largely determined by three major factors: the expansion of the universe, the initial density of matter on a cosmic scale, and the interactions occurring between multiple cosmic scales. These elements determine the formation and evolution of galaxies. Internal processes within galaxies, sometimes referred to as galactic physics, have little effect on the creation and growth of galaxy clusters. Gravity is the only major force at play throughout the history of the cosmos. The role of redshift in galaxy observation. One of the simplest methods to identify a large number of galaxies within the same field of view at identical redshifts, distances, has been employed. Redshift occurs because light emitted by a moving object shifts toward longer wavelengths. This effect, known as the Doppler shift, causes light from receding galaxies to shift toward the red end of the electromagnetic spectrum. When a galaxy moves away from us, its emitted light is redshifted, meaning the spectral lines in its spectrum move toward longer wavelengths. Astronomers measure this redshift by analyzing the spectrum of light arriving from the galaxy. By examining the spectrum and detecting significant shifts in the spectral lines, they can determine the velocity at which the galaxy is receding and estimate its distance. The degree of redshift is represented by the parameter z, which expresses the ratio of the measured wavelength to the wavelength emitted by the galaxy. A higher z value indicates a greater redshift, and by measuring the redshifts of numerous galaxies, astronomers can map the distribution of galaxies throughout the universe. This data also provides insight into the expansion of the universe and the evolution of galaxies over time. Galaxy clusters and the forces of gravity. Clusters of galaxies have been observed moving at velocities ranging from several hundred to a few thousand km/s relative to each other. This method helped in the discovery of nearby galaxy clusters, such as the Coma cluster and the Virgo cluster, which are heated by phenomena like the collision of fast-moving gas clouds or intense star formation processes that release X-rays. The study of galaxies and their clusters plays a crucial role in understanding the broader cosmic structure and the history of the universe. These clusters of galaxies provide valuable insights into the nature of cosmic evolution, as well as the interplay between dark matter, normal matter, and the forces of gravity that shape the universe. The discovery of distant galaxy clusters, along with the measurement of redshift, has enabled scientists to track the movement of galaxies over vast distances, shedding light on the ongoing expansion of the cosmos. As these galaxies move away from us, the redshift in their light provides essential information about the speed at which they are receding. Exploring the universe's mysteries. This observation of redshift is not only a way to estimate the distance of galaxies, but also an indicator of how the universe has been expanding over time. By studying the various redshifts of galaxies, astronomers can effectively chart the growth and distribution of the universe's structure across different epochs. These measurements reveal the dynamics of cosmic evolution, helping us understand how galaxies, stars, and other astronomical objects formed and evolved throughout the universe's history. The processes that govern the movement and interaction of galaxies within clusters are highly complex. In galaxy clusters, the galaxies are gravitationally bound together, and their individual movements are influenced by both their own mass and the mass of the surrounding objects. The motion of galaxies within clusters is a key factor in the overall structure and behavior of the universe. The gravitational interactions between galaxies can lead to the merging of galaxies, forming larger structures over time. The formation of supermassive black holes. These galactic collisions and mergers are important processes that drive the growth and evolution of galaxies. shaping their final structure and composition. While the study of individual galaxies is important, understanding the larger-scale structures formed by galaxy clusters is equally significant. The interaction of galaxies within clusters can also lead to the formation of supermassive black holes at their centers, which play a pivotal role in regulating the growth of galaxies. These black holes, along with the surrounding gas and dark matter, contribute to the overall dynamics of galaxy clusters. Final thoughts and what's next? Through the continuous exploration of the universe with advancements in technology, like the James Webb Space Telescope, astronomers are able to probe deeper into space than ever before. The telescope's ability to capture light from distant galaxies, including those formed in the earliest moments of the universe, will provide unprecedented views into the formation of the first galaxies and the overall structure of the universe. This will help us uncover not only the origins of galaxies but also the processes that led to the emergence of stars and planets. As we continue to push the boundaries of our knowledge and improve our observational capabilities, the insights we gain will bring us closer to understanding the origins of the universe. Whether it's through the detection of ancient galaxy clusters or the study of the cosmic microwave background, each discovery helps piece together the puzzle of how the universe evolved from its earliest stages to the vast and complex structure we see today. This journey into the heart of cosmic history is a testament to the power of scientific discovery and the quest for knowledge. The mysteries of what came before the Big Bang and how the universe began are still far from being fully understood. But with tools like the James Webb Space Telescope, we are steadily uncovering new pieces of the cosmic puzzle. As we continue to make strides in our understanding of the universe's origins, one thing remains clear. The more we learn, the more we realize how much there is yet to discover. From the tiniest fluctuations in the early universe to the vast structures of galaxies and clusters, the universe holds endless wonders waiting to be explored. With each new discovery, we are one step closer to answering some of the most fundamental questions about our existence. If you find these cosmic revelations intriguing and want to stay informed about the latest breakthroughs in space research, make sure to subscribe to our channel. Join us as we continue to explore the mysteries of the universe, bringing you the most up-to-date information and the most exciting discoveries. Don't forget to like this video and turn on notifications so you never miss out on the latest space news. Understanding the significance of galaxy clusters. As we delve deeper into the study of cosmic structures, the significance of galaxy clusters cannot be overstated. These massive conglomerates of galaxies serve as natural laboratories for studying the fundamental forces that govern the universe. Each cluster provides a unique insight into how gravity and dark matter interact on the grandest scales, shaping the evolution of the cosmos over billions of years. Through the lens of the James Webb Space Telescope, scientists have the opportunity to look further back in time, reaching galaxies and clusters that formed just after the Big Bang. These early structures are vital to understanding the initial conditions that led to the formation of the more familiar galaxies we observe today. The role of the James Webb Space Telescope in uncovering cosmic secrets. The James Webb Space Telescope, JWST, continues to revolutionize our understanding of the universe, providing unparalleled insight into the earliest moments of cosmic history. Unlike its predecessor, the Hubble Space Telescope, JWST operates primarily in the infrared spectrum, enabling it to peer through cosmic dust and observe distant galaxies, star-forming regions, and other cosmic phenomena that were previously hidden. This ability to detect faint infrared light allows scientists to look back further in time than ever before, reaching into the very infancy of the universe. With its ability to capture the oldest light, JWST is offering a closer look at the formation of the first stars and galaxies, shedding light on the mysterious period known as the Cosmic Dawn. Probing the early universe and cosmic evolution. One of the most exciting prospects of JWST is its potential to probe the epoch of reionization, a crucial period in the universe's history that occurred roughly 400,000 years after the Big Bang. During this period, the universe transitioned from being opaque to transparent, as the first stars and galaxies began emitting radiation that ionized the hydrogen gas that permeated the cosmos. This transition is vital for understanding how the universe evolved from its dense, hot state to the vast, structured cosmos we see today. JWST's ability to study the earliest galaxies formed during this era provides crucial data on the processes that led to the development of the cosmic structures we observe now, such as galaxy clusters and the formation of supermassive black holes. Unveiling the first galaxies and stars. JWST's ability to detect galaxies formed only a few hundred million years after the Big Bang offers a unique opportunity to study the formation of the first stellar populations. These early galaxies are expected to be vastly different from those we see today, containing lower levels of heavy elements and exhibiting irregular shapes due to their rapid star formation. By examining these galaxies, scientists can uncover the physical conditions that allowed for star formation in the early universe, how gas was converted into stars, and how early galaxies evolved over time. The first stars, often referred to as population 3 stars, are theorized to be composed mostly of hydrogen and helium, the lightest elements formed in the Big Bang. These stars were much larger and hotter than the stars we see today, and their formation marked a pivotal point in cosmic history. When these stars died, they seeded the universe with heavy elements through supernova explosions, providing the raw materials for the formation of later generations of stars, planets, and even life. The importance of dark matter and dark energy. Dark matter and dark energy are two of the most mysterious components of the universe, and their roles in cosmic evolution remain a subject of intense study. While we cannot observe dark matter directly, its presence can be inferred from its gravitational effects on visible matter. JWST's observations of galaxy clusters, gravitational lensing, and the distribution of galaxies at various redshifts will help scientists map the distribution of dark matter and understand its role in shaping large-scale cosmic structures. Dark energy, on the other hand, is thought to be responsible for the accelerated expansion of the universe. Understanding the interplay between dark matter, dark energy, and ordinary matter is essential for developing a complete picture of how the universe has evolved and will continue to evolve. By studying galaxy clusters and their evolution over time, JWST will help refine our understanding of dark energy's role in the cosmos, providing critical insights into the ultimate fate of the universe, future prospects, and expanding our horizons. As the James Webb Space Telescope continues to collect data, it promises to answer fundamental questions about the origins of the universe, the formation of galaxies, and the nature of the dark components of the cosmos. Each observation brings us closer to understanding the processes that shaped the universe we observe today, offering new perspectives on the cosmic timeline. The insights provided by JWST will not only deepen our understanding of our place in the universe, but also inspire future generations of scientists and explorers. The continuous exploration of space, driven by advancements in technology and the commitment to discovery, will undoubtedly reveal even more cosmic mysteries, pushing the boundaries of human knowledge further than ever before.